Okay, welcome back. Today's lesson is, again, translation, dilation, and reflection of parent functions. Now, before we get into this lesson, I need to give you guys some, wouldn't call it background information, but let's go ahead and get this in our notes. Super important information. Okay, first, definition of a function. Now, this is not the precise definition, guys. This is a baby definition, okay? Soon I will tell you guys to take this definition out of your notes and replace it with the proper definition. And the most important definition in this class is the definition of what a function actually is, okay? So we're going to be looking at the whole course. The whole heart of this course is trying to understand what is a function, okay? So first definition of a function, the most important definition in this class, I can say this, probably one of the most missed definitions on tests and quizzes. So make sure that you guys take the time to know this. It's kind of simple. If you were in class Thursday, you guys already saw this and should already have this in your notes. But for those of you that did miss class, go ahead and put this in your notes. Super important. A function is, and if you've already seen this, guys, just fast forward the video to the part you need to watch. A function is a machine, okay? A function is a machine. It's something that grinds. It's something that burns. If a function, I use this analogy in class. If a function were a toaster, it toasts something. If a function is a car, it gets you from point A to point B. If a function is a tree grinder, okay, it grinds something, okay, it acts on something. A function is a machine with an input called the domain and an output called the range. Okay, so let's try to understand this for a moment. Input called domain, output called range. Okay, so I love the toaster analogy. A machine. Okay, so a function is a machine. A function is the toaster. Okay, it acts on something. It burns something. Okay, a function is a machine with an input called what? Domain. So if a function were a toaster, what is the input called? Well, there's many inputs for toaster. You could have what? Bread. You could have Pop-Tarts. Okay, the domain is what goes in. Okay, so bread is domain. Pop-Tarts, domain. Maybe waffles would be domain. I guess you can toast waffles. So input called domain, output called range. So if the input is bread, the output or the range would be toast. Okay, so input, domain is bread, range is toast. Okay, so the function is the toaster itself. Now, before we get into the lesson again, you must understand that algebra is divided into 3 branches, okay? And this is going to help you guys understand what's actually happening in this course. So this is all extra information. I would recommend not writing this down because I'm going to be going through this many times this semester explaining this, so I'd rather you just listen. Expressions, equations, and functions. So if I were to divide algebra into 3 branches, okay, you have your expressions, you have your equations, and you have your functions. Okay? And everything we learn in algebra can be put into one of these categories. Now, starting with equations, you guys have already looked at equations this semester. Looking at the absolute value equation, absolute value x minus 3 equals 5. We have 2 things that make this true. Remember, we find a center. Okay? The center is what? 3, and the distance either way is 5. 3 to go to the right is to add, we get 8. To go to the left is subtract, we get negative 2. So we get solutions of 8 and negative 2, and we graph these solutions on the x-axis, okay? Remember, okay, so I'm going to erase this so we can see. How many types of variables do equations have? Notice, we just see how many variables in this equation. We just see one variable, x, okay? So we have an x-axis, one dimension, okay? And the values that make this equation true are the values 8 and negative 2. Okay, so let's see. If we put 8 in, 8 minus 3 is 5, the absolute value of 5 is 5. If we put negative 2 in, it also makes it true. So you agree 8 and negative 2 make it true. All other numbers make it false. For instance, a number 100 way up here. Okay, if we put 100 in, 100 minus 3 is 97. The absolute value of 97 is not 5. Okay, so what values make this true? 8 and negative 2. We mark these locations on the x-axis with points. Now, functions. okay, have two types of variables. So if I write y equals the absolute value of x minus 3, you guys remember from the last video that minus 3, or subtract 3 inside, means 3 units. 3 units to the right. Okay, I don't think the video can pick that up. 3 units right. Okay, so this means it's V-shaped, 3 units to the right. This is our vertex, and it has a V shape. Okay, and okay, notice in the equation we have one type of variable, x. That's one-dimensional x-axis. In the function, how many types of variables do we have? Well, we have x and we have y. This is 2 dimensions. So we have an x-axis, we have a y-axis. In the equation, 8 and negative 2 make it what? True. All other numbers make it false. What does this v represent? Okay, this v represents an infinite set of points. An infinite set of points that make this function true. I will show you what this means in a minute. So we graph what makes it true. Okay? And it's represented by a V shape in 2 dimensions. We have 2 variables, 2 dimensions. We have an x and a y axis. Now, equations are either true or false. And we solve for the values that make it true, or we graph the values that make it true, namely the values, in this case, 8 or negative 2. Functions are also true or what? False. And we graph what makes the function true in 2 dimensions. Okay, functions have 2 types of variables. Okay, so again, this v represents what makes it true. I will show you in a minute what that means. Over here on the expressions, expressions have values. Okay, so if I write the absolute value of x minus 3, and I asked you what the value of this expression is, well, hold on. Before we even do this, notice, do you see equality in the expression? Okay, do you see this equal? Do you see the equality sign in an expression? No. That is how you know that you're looking at expression. It has no equality. It's just something written without equality. Okay, so it just has a value. So if I ask you, what is the value of this expression? You would tell me, I don't know. Why do you not know? Because I have not told you what x is. Okay, so expressions have values. The values are either known values or they are unknown. Watch. If I say the absolute value of 8 minus 3, okay, this expression, you know its value because you see both numbers in it. 8 minus 3 is what? 5. And the absolute value of 5 is 5. So you know the value of this expression is 5. Okay? This expression, you do not know its value until I give you the value of x. So if I say x is 7, well then you know the value is 4 because 7 minus 3 is 4. And the absolute value of 4 is 4. So again, expressions have values that are either known values or unknown values. Okay? Known values means you read it. Unknown values, you have an x or a variable in it, and you cannot evaluate without knowing the value of x. Okay? So in the expression, again, you don't know the value of this top expression because it has an x until I tell you what x is. Okay? Back to the equation and the function, the 2 most important topics in this class. Or maybe say this first. You guys will learn algebra this way. Starting with expressions and resulting in what? You will learn the expressions first, and then you will learn the equations, and then you will learn the functions. Expressions lead to the value. Learning expressions leads to the ability to solve equations, and learning how to solve equations leads to the ability to graph functions. Or more specifically, to simplify or factor expressions leads to the ability to solve equations, and the ability to solve equations leads to the ability to graph functions. Now, over here, quick little analogy. So if I write the absolute value of x minus 3 is less than or equal to 5, reminding you guys, this is an and statement, so we write what? This is an equation, has one type of variable. We write x minus 3 is less than or equal to 5, and what? X minus 3 is greater than or equal to negative 5. Remember, flip the sign, add 3, we get x is less than or equal to what? 8, and add 3, we get x is greater than or equal to negative 2. Okay? Remember, and statements have to be compressed. X between 2 values. Between the values negative 2 and 8. Remember that the signs always point the same direction, or the signs point to the left. If you forget, look here. X is less than or equal to 8. X is what? Greater than or equal to negative 2. Okay? It's pointing towards negative 2 still is. We read this. What is the key word? The key word is between. Okay? So we read this as x is between negative 2 and 8. And we graph this. How many variables are in the equation, or specifically inequality here? Okay, this is technically an inequality, but falls under the realm of equations because it has one type of variable. Okay, the solutions are everything between -2 and 8, and so we close it at 2, we close it at 8, everything between. We have just graphed the solutions. So what is this? What is this that you're looking at? You're looking at the graph. You're looking at the graph. You're also looking at the solution set. How many numbers are in this set? Hopefully you say, based on previous videos, okay, that there are infinitely many numbers in this set. Pick a number that is between -2 and 8. Okay, so I'm going to pick for you. How about 5? Is 5 between -2 and 8? Hopefully you say yes. So 5 makes this equation true. All of the numbers in this infinite set make the equation true. For instance, 5. Put in 5 for x. 5 minus 3 is 2. The absolute value of 2 is 2. And is 2 less than or equal to 5? Yes. Okay, so all of these numbers, one-dimensional solutions, make the equation true. Now, let's look at this function, y equals the absolute value of x minus 3. Notice there are two types of variables. Okay, again, this is function. One type of variable is in the realm of equations. Okay, so again, two types of variables. We have an x-axis and a y-axis, and the minus 3 means 3 units to the right. Okay, so we're going to move 3 units right, and we're going to put a point, and we're going to graph some more points. Okay, need to erase this here. So we have a point here, we have a V shape. Okay, and I said that this V represents what makes this function true. Now the difference is, in the equation, again, one type of variable, one value. Okay, so we put in one value, 5 for x. In the function, we have two variables. Okay, again, x-axis and y-axis. And every point, again, this is an infinite set of points, is represented by two values. Okay, so this vertex point is the point 3, 0. Okay, now it has both an x value and a y value. And again, the points on this function the points that are on this, function, make the function true. Okay, again, how many points in this solution set or this graph? Infinitely many. What is this over here? This V shape is also a solution set or a graph. Okay, again, we graph what makes it true. Now, every solution has two parts. It has an x value and a y value. So this point on the function at 3, 0, if we put it in, notice the x value is 3 and the y value is 0. So we're going to put in 0 for y. Watch, this makes it true. Put in 0 for y equals the absolute value of 3 for x minus 3. Is this true? Yes, because 0 is equal to the absolute value of 3 minus 3. 3 minus 3 is 0, absolute value of 0. This is true. Okay, now, what is another point on the function? Another point on the function. What about the point here? This point is at 4, 1. So if we put these values in, the x value is 4, the y value is 1. The y value is 1, so we're going to put in 1 for y. The x value is 4, so we're going to put in 4 for x. We get 1 is equal to the absolute value of 4 minus 3. Is this true? Yes. Okay. 4 minus 3 is 1, absolute value of 1 is 1. Now, okay, so the graph represents what makes it true. In this case, we have a one-dimensional graph. In this case over here on the function, we have a two-dimensional graph. What about everything else? Okay, going back over here, everything else makes it false. So if we pick a number that's not in the graph, it makes it false. So if we pick a number down here may be -100, way down here. You put in -100 minus 3 gives -300. I'm sorry, -103. The absolute value of this is 103. Is that less than 5? No. Every other number makes it false. If we pick a point that is not on this V, it makes the function false. For instance, if we pick a point down here, maybe the point -3, -1. Okay, the point -3, -1. This point is not on the function, the V. Okay, so this point would make it false. For instance, -3, -1 has an x value of -3 and a y value of -1. So if we put in -1 for y, we get -1 is equal to the absolute value, and put in -3 for x, -3 subtract 3. Is this true? Hopefully you say no. Is -1 equal to the absolute value of -6? No. The absolute value of -6 is not equal to -1, so we see that any other points make this false. So again, what makes it true? The points that lie on the function itself, the V. Okay. All right, so again, recap. Expressions have values. Equations are true or false. We solve for the values that make it true, and we graph those values on a one-dimensional x-axis. Functions are true or false. We solve or we graph what makes them true, and we graph this on a two-dimensional grid because we have two types of variables. Okay, so that hopefully sums it up. Now, as far as the layout of the course, okay, so everything's going to be studied in terms of expression, equation, then function. You ask, well, then why are we starting with functions? Okay, first, before we actually go to expression and then equation, you have to get some basic concepts of functions first, and then we're going to start the course. Okay, so we still haven't even really started this course yet. We're just kind of getting some foundational information down. Okay, so now, function is what? A machine with an input called the domain and an output called the range. Okay, let's look at the first function that we're dealing with, and we're going to look at this in terms of a machine. Okay, this is the function y equals the absolute value of x. Okay, and again, from the last video, this is the absolute value parent function. Now, I told you where the points were located on the last video. This video, we're not going to assume that we know where the points are located. We're going to develop this in terms of what is a function. A function is a what? Machine, okay, with an input called the domain and an output called the range. So what we're going to do is we're going to set up a t-table. Okay, so absolute value parent function, we're going to set up a t-table out here. And we need to figure out, maybe this is not a good spot. I need a spot where, here. Let's put this here. And we're going to put the t-table over to the left. Okay, x, y. Now, no, that's not even good. How about here? X, y. Okay, so what is this? I'm circling it. What is this? Circled. This is the function. Okay, y equals absolute value of x, the equation of the function. What is this? What is this? This is a machine. Okay, it's a car. Okay, so let's treat this like a car for a moment, and let's try to understand this definition a little better. So if I say car is a machine. Okay, and I need to know domain of car. Okay, domain of car. Domain is what goes into a car. Okay, so what is the domain of a car? Okay, my question is, what do you put into a car? Well, hopefully you think, well, car needs what? We put in gas. What else goes into a car? So we're writing here, car is the function. Car is the function itself. We're writing the domain of car. Domain is equal to what? Gas goes into a car. What else goes into a car? Hopefully say oil. What else goes into a car? Windshield wiper fluid. Okay, what else goes into a car? You might say brake fluid. Okay, what else? Antifreeze. Okay, what else goes into a car? What else goes into a car? Someone said today, air pressure. Okay, yes, we have air going into the tires. Okay, so there's many things that go into a car. Many, many more. Okay, so we have domain of car is what goes into the car. We also have range of the car. The range of the machine is what the machine puts out. Okay, so what is the range of a car equal to? Okay, so we think for a minute. What does a car put out? Okay, you put these things in, it gives you something. Puts out something. It puts out, well, it gets you from point A to point B. So how about we say A to B? It gets you somewhere. And that's one thing that a car puts out. It puts out power, okay, to get you from point A to point B. What else does a car put out? Students struggle with this. Okay, so what else does it put out? Let's see. Heat. Oh, yeah, heater. What else? AC. What else does a car put out? Think. What else does a car put out? It puts out, someone said, pollution. Yes, it does put out pollution. It does. What else does a car put out? How about radio? Okay, radio is in the range. What else does a car put out? What else is in the range of car? Okay, range of car would be radio. How about lights? Okay, so headlights. Okay, many things that a car puts out. So the domain is what goes into the car: gas, oil, windshield wiper fluid, and the range would be what comes out: heat, AC, pollution, radio, lights. Okay, so hopefully you get the concept that functions have an input called the domain, okay, and an output called the range. This function is a machine, okay, and we're going to be looking at this in terms of machine. Now, I'm going to draw the machine over here. Okay. This machine is going to have a name. I'm not going to name it yet, but the input, what goes into the machine, is going to be called what? Domain, and what comes out of the machine is going to be called range. Now, here. Okay, if we think in terms of car for a moment, can you put anything into a car that you want? Okay, do we put milk into the gas tank? No. Okay, do we put in, don't do this, okay, so if you put in sugar, okay, that would be bad, okay, that would break the engine. Okay, so don't put sugar, don't put milk into a car. Are there certain things that a machine will accept and certain things that it will not accept? Yes. Okay, so this function is a machine. There are certain things that you can put in, well, this is not a good example. Okay, this machine will accept anything, all right? Certain machines will accept anything, but you have to ask yourself, what is the domain of this machine? You have to ask what can go into the machine. Now, in this class with functions, what are we going to be putting into the machine? We're going to be putting in numbers. And what's going to be coming out? Numbers. Okay, so input is numbers, output is numbers, but not every machine will accept any numbers. So we have to first ask, what will this machine accept? Now, I'll give you a big hint. This machine will accept, again, any number. But soon you will see machines that will not accept any number. Let's think for a moment. Okay, we're going to call this the absolute value machine. Whatever goes into it gets crunched, and then, we get the absolute value of whatever we put in. So we put in a number, the machine takes the absolute value and gives us an output. So you start thinking, okay, what numbers can go into this machine? Well, are there numbers that can break this machine? Well, I've already told you that the machine will accept any number. Watch. Can we put in 2 into the machine? Yes. Okay, if we put in 2, we get crunch, absolute value of 2 is what? 2. So we get an output of 2. So 2 works. You start thinking. Can 0 go into the machine? That's always the problem child right there. It's 0. Can 0 go into the absolute value machine? Yes. We put in 0, crunch, absolute value of 0 is what? 0. Okay. Now, can a negative number go into the machine? What about negative 4? Can negative 4 go into the machine? Yes. If we put negative 4 in, the absolute value of negative 4 is what? 4. So we get an output of 4. Okay, you're starting to see, looks like any number can go in, and that's the case. What about negative 100.23? Can negative 100.23 go into the machine? Yes. If we put in negative 100.23, we get what? Crunch, we get 100.23. It makes, basically, the machine is making every number positive, okay, or leaving it alone. So we're going to go over here. The input. The input of a function, go ahead and put this down. Input is called domain. Okay? And we're going to choose. Now, you can't just choose anything you want. You have to, your domain can only follow what the function will accept. Okay, so you can only choose numbers. And what I'm saying is, you can only choose numbers that the function will accept. Now, for this function, we start with something basic. The absolute value function, the absolute value function will accept any number. So does it matter what we choose for domain? Hopefully you say no. So we're going to pick some basic values. How about 0? Okay, and 1, 2, and 3. We put in negative 1, negative 2, and negative 3. We're going to put these values, these 7 values, into the machine and see what happens. So hopefully at this point you can follow. If we take 0 and put it into the machine, crunch, we get what? 0. So we put in 0. And what do we get back out? We get back out 0. Out here, these values are called the range. Okay, here, let me write it bigger so you guys can see. This is the range. Okay, so output's a range, input is domain. Now, if we put in 1, okay, we get an output of what? 1. If we put in 2, the absolute value of 2 is what? 2. If we put in 3, we get what? 3. If we put in negative 1, okay, so negative 1 goes in, absolute value of negative 1 is 1. So we put in negative 1, we get an output of 1. Put in negative 2, you get an output of what? 2. You put in negative 3, you get an output of 3. And now, what have we just created? A list of ordered pairs. We can graph these points on the function. So we have the points what? 0, 0. 1, 1. 2, 2. 3, 3. Just graphing these points. 1, 1. 2, 2. 3, 3. What else? Negative 1, 1. Negative 2, 2, and what? Negative 3, 3. Okay, so we graph it, and we get this V shape. Hold on. Can we connect the points? Okay, hold on. Before we do this, don't just connect the points. How many points did we just graph? We graphed how many? We graphed what? 7 points. Okay, I'm going to erase this. We graphed 7 points. Can we connect them? Yes, I will explain in a minute. Okay, now before we do this, what numbers can go into this machine? Now, we've already established, well, it looks like any number can go in. The machine will accept any number. No, there is no number that will break this machine. I tell students, well, it's kind of like a tree grinder, you know. Does a tree grinder really care what you put into it? Not really. Can you put gas into it? Yes. It won't really grind anything, but you pour it in there, it doesn't really do anything. You put tree into tree grinder, what does it do? It crunches the tree up. Okay, but that's why I say don't get your arm stuck into a tree grinder, because does it care what it grinds? No. It will grind nearly anything, okay? I think there's certain things that might break it, maybe a metal rod or something, but the concept is this. This function is sort of like a tree grinder. Whatever you put in, it doesn't really care. It will take the absolute value of any number. So again, over here, what numbers can go into this machine? Hopefully you say any number can go into this machine. So we say that our domain is all real numbers. This is the symbol for any number can go into the machine. Now our outputs are a little different. Notice, on our outputs, the values that are coming out. Question, do we have negative numbers coming out? Nope. Okay, what do you notice about the numbers that are coming out? Hopefully you say, well, these are positive numbers. Okay, our range is all positive numbers. And what else? And what else? 0. Okay, so all positive numbers, also 0. Okay, 0 is not considered to be positive or negative. So we say that our range is all positive numbers and that our domain is any number. Okay, so we notice the outputs are positive. Now, can we connect these points? My question is, can we connect the points? The answer is yes. But when you connect points, how many points are you graphing? Okay, when you connect points, you're graphing how many points? Infinitely many. So what makes you say that all these other points can follow the same pattern? Well, we watch. Look over here. I'm going to erase 0, 0. Okay, if we put in, what if we put in 0.1, what do we get? Well, if we put in 0.1, the absolute value of 0.1 is 0.1, so we get 0.1. If we put in 0.2, what do we get? Well, we get 0.2. Watch. Here's 0.1, 0.1, and here's 0.2, 0.2. Okay, could we put in 0.3? Yes. If we put in 0.3, what do we get? 0.3. Okay, so we have 0.3, 0.3. You start to see, do you notice that the other points are following the same pattern? Yes, and why can we connect these points? Why can we connect the points? We can connect the points because the domain is what? Any number. Are there infinitely many points between any two points? Yes. Can we put in 0.33? Yes, we get 0.33. Can we put in 0.33333? Yes, we get 0.33333. All of these points lie very, very close. Okay, and how many points can we graph? Infinitely many, and you'll find the other points follow the exact same pattern. So the question is, why can we connect the points? We can connect the points because any real number can be put in to the domain, or any real number is in the domain. Any real number can be put into this function leading to an output. And since there's an infinite number of numbers that can go in leading to the same pattern, it forms a solid set. Okay, so we have an infinite set of points. So here, I said it better in class, I think. You have 0.1, 0.1, point what? 0.1, 0.01, 0.001, 0.001. Okay, so you end up with, looking at this mess right here, you've got 0.1, 0.001, 0.0001, and the points lie infinitely close, and you can continue to do this, okay? And infinitely close. We've talked about this before. Now, so you get this V shape. An infinite set of points. Okay, wow. All right, this should always blow your mind when this happens. Okay, now, we focus on these 7. I think what I'm going to do is conclude the video at the end of this discussion, okay, of the absolute value parent function, and then maybe come back in the next video and pick up on this because the video will be very, very long. Okay, so now we're going to establish visually what the domain and the range of this function are. Okay, now this, you may not quite understand this. You may not quite understand this yet. Here, so we have absolute value of x, y equals absolute value of x. We're going to establish domain and range visually. So we have 0, 0, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, and negative 3, 3. Okay? Well, I guess I could probably just finish the lesson. So we're looking at, here, let's just do this. This would be better. Instead of here, let's just pick it up this way. Okay, so we're looking at let's just go straight to translation, dilation, reflection. Let's go ahead and start the lesson. I'll just finish it in this video. Translation. Translation is a slide. Okay. Dilation is a stretch. And reflection is a flip. Okay. Now, starting with translation or slide. We looked at this in the last video. So y equals the absolute value of x minus 3 plus 1. Okay. Now, slide, translation. Something is being added or subtracted. Okay. Something is being added or subtracted. Notice 3 is being subtracted inside, 1 is being added outside. From the last video, you should recognize this as 3 units. 3 units right. It's the opposite of what's inside. 3 units right and 1 unit up. Okay, it's exactly what makes sense on the outside. What we're going to do in this video is write the vertex. Okay, so we're going to do this a little differently. What I want you guys to do is write the vertex. Notice, every point is going to slide 3 units to the right and 1 unit up. So notice, we're going to take the opposite of what's inside. So if we have minus 3, the vertex will be the opposite of what's inside. So minus 3 becomes what? Positive 3. This is your x value. And what's on the outside, leave it alone. The positive 1 will stay positive 1. So we get the point, positive 3, positive 1. So what did we do? We changed the value of what's on the inside, and we left alone what's on the outside. So we changed this to positive 3, and the point is positive 1. Now, we graph the function this way. Okay, so we're going to actually use what we call a pattern here. If you remember in the last video, when we graphed functions, every member of the family had the same size and shape as the parent. This is going to save us time. Watch. Let's graph the vertexes where? At 3, 1. Now, you do not have to graph the parent function every time, just the member of the family. Okay? So 3, 1, let's label the vertex. Okay, the vertex is where? At 3, 1. Okay, so make sure you label the location of the vertex at 3, 1. And notice, the parent function has a specific pattern. And if you go back, if you didn't realize this, go back to the last video and rewatch it if you have to. The parent function and the function that we graph here have the same size and shape, meaning they have the same pattern. In the parent function, right 1, up 1, right 1, up 1, right 1, up 1. Okay, so every function in the family will have a very similar pattern to the parent. So if we go right 1, up 1 in the parent, right 1, up 1, right 1, up 1, we can graph the member of this family using the same pattern. So we're going to go from this point, we're going to go right 1, up 1, and put another point. Do it again. Go right 1, up 1, and put another point. Go back to the vertex, same thing. We can also go left 1, up 1, left 1, up 1, and left 1, up 1. Notice I'm focusing on up 1, up 1, up 1. Okay? We're not focusing on the horizontal, we're focusing on how far we go up. You always go right 1. You always go left 1. That never changes. But this vertical distance will change problem to problem. For these problems right now, we're going what? Up 1, up 1, up 1. So, from the vertex, right 1, up 1, right 1, up 1, put more points. Go back to the vertex, do the same thing going the other way. Left 1, up 1, okay? Left 1, up 1, okay? And a minimum of 5 points is required. Now go ahead and graph the function. And now we're going to analyze what we call the domain and the range visually. Okay, so you looked at domain and range looking at input and output, okay, on the function. Now we're going to analyze domain and range visually. Okay, so this is a little tricky. Domain is left to right, and range is bottom to top. Okay, so domain, range, starting with domain, left to right. So if you think of this, okay, this is domain, left to right, left to right, left to right. Domain is horizontal, and if we go to range, range is what? Vertical. Okay, vertical will be bottom to top. Now, back to domain. Domain is what? Horizontal, left to right, or I tell students negative to positive. Now, way out here, concept forever left. What is forever left idea? Forever left idea is the concept of negative infinity. Okay. Now over here, far right concept. Far right concept is positive infinity. Okay. So if we go forever to the right, and when I mean forever left, I mean beyond the earth, beyond outer space. Forever left. Okay. This is the idea of negative infinity. Forever right. outside the atmosphere, beyond outer space. Forever right is the concept of positive infinity. Now, we analyze domain left to right. Okay, so way out here, way out here, way out here. The question is there function? So when we do domain, we run along the x-axis, and we answer yes or no if there is a function above us. Let me start here. Okay, so my question, is there function above us? The answer is yes. This is a one-dimensional analysis of a two-dimensional object. Okay, so yes or no. Starting here, yes or no. Do we have function above us? Yes. Okay, there's a point here. Okay, yes. If we run along the x-axis, we're focusing on domain. So running along the x-axis, do we have function? Yes, 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 yes. As long as we're answering yes, this is inside the domain. If we answer no, then it's not in the domain. So answer yes or no. Yes, 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 yes. Okay, this function, notice, does the function go left forever? Does the function go left forever? Yes. Does the function go right forever? Yes. We're not looking up or down, just left or right. So way out here, forever left, here, way out here, way out here, way out here, here, way out here, way out here. Yes or no? Is there function above us? Is there function above us? Yes. If you say, no, well, hold on. Doesn't this function go up and left forever? So way up into the sky, past the atmosphere, way up there. Is there a point way up there? Yes. So we're answering yes, 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 there's function. Is there function here? Yes, 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 and it goes forever right. So we see everywhere on the x-axis we have what? Function. So we say that the domain is from what? The concept of negative infinity to positive infinity. So our domain is what? Domain is left to right. Domain is negative infinity to positive infinity, or otherwise stated as what? Negative infinity to positive infinity is all real numbers. Now, over here, what will these machines accept? These machines will accept what? Anything. So our domain is from negative infinity to positive infinity. This means all numbers that your mind can think of, from negative infinity to positive infinity. Now, looking here, the domain is negative infinity to positive infinity of this member. So does this family member have a domain of all real numbers? Yes. Does the parent function have a domain of all real numbers? Yes. Every member of the absolute value family, whether it's a member or the parent itself, will have a domain of all real numbers. Meaning that, what? In terms of the machine, any number can go into this function. Question. Down here, way down on the x-axis, way down here, negative 1 million, way out here. Okay, so way out here on the x-axis. I don't have a lot of space, guys, so I'm trying to think in terms, generalize with me. Way out here at negative 1 million. Can negative 1 million go in? This is the x-axis. Can negative 1 million go in for x? Yes. Negative 1 million minus 3, yes. Okay, and then we can take its absolute value and add 1. So any number can go into this machine. That domain is all real numbers. Now, range. Range is bottom to top. Okay, bottom to top. Or think of it this way. Negative to positive for domain is left to right. And range, negative to positive. Negative, what's forever down? Forever down, this concept down here is negative infinity. Forever up, the concept up here is positive infinity. Now, we're going to do the same thing vertically, starting at the bottom at the negative. Okay, so running along the y-axis, my question is yes or no, do we have function down here? Yes or no? So you look, is there function left or right of us? No. Okay, so we're running up. No, no. You say, why are you saying no? Well, the function's up here. So down here, is there function left or right of us? No, there's no function. Okay, so we're running up, running up. What do we have? No, there is no function. No, 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 no. Yes. Okay, what happened? There's function right here to the right of us. Okay, what is this height? This height is what? 1. Look at the y value of the vertex. What is the y value of the vertex? The y value is 1. Okay, so we say that the range starts at a height of 1, and then what do we have past 1? We have what? Yes, 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 yes. There's function everywhere to the left and right of us. So again, down here, do we have a yes or no? Is there function left or right of us? No, 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 no. Yes. Why do we have a yes at 1? Because there's function to the right of us. So we say that the range starts at 1, and does it go up forever? Yes, 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 yes. Does the function rise forever? Yes. So it's a one-dimensional analysis of a two-dimensional display. So we're just looking at the vertical. Starts at 1, goes up forever. So we say from 1 to what? Infinity. The question is, do we include the 1? Yes, we include the 1 because we have a point at 1. So we put a bracket. Okay, when would we not include the 1? Let's look. if this point were an open circle, okay, and we already did piecewise function, so this should be familiar. If this were open, we would have a parenthesis, meaning do not include. But since this is closed, we have a point here, and we put a bracket, include the 1. Now again, domain is left to right, negative to positive. Range is bottom to top, or negative to positive. Okay, now, next function. Okay, where's my... Oh, so much information in this lesson, guys. This is a heavy lesson, okay? But super important lesson. Not, I wouldn't say necessarily hard once you get it. I think it's more geometrical. Let's look at this function. Y equals 2 times the absolute value of x minus 3. Or let's change this. X plus 2 minus 1. No, let's change that to x plus 4 minus 1. Now, we need to find first a vertex. Now, looking over here, translation or slide is something's being added or subtracted. So notice in the function, 4 is being added, 1 is being added. The 4 and the 1 result in a translation or a slide on the function, either left and right, up and down. We have, in this case, 4 units left, 1 unit up. Okay? Now, this is your translation, these two numbers. Now notice that we have another thing here, the 2. The 2 is being multiplied. This results in a stretch, or called a dilation. So the dilation is a stretch. Something is being multiplied. Okay? So dilation means something is being multiplied. So circle the 2 and write dilation. Okay, we'll talk about what this means in a minute. We're going to ignore it for now. Let's start with the translation. So I want you guys to write vertex. Okay, and the vertex is the opposite of what's inside and exactly what you see on the outside. The opposite of what's inside. So the opposite of 4 is what? Negative 4. And exactly what you see on the outside is what? Positive 1. Let me help you tie this into something you already know. Watch this. If I write y equals 2 times the absolute value of x plus 4 plus 1, let's take the 1 and move it back over with the y. So we end up with what? Y, then opposite the 1, which is minus 1, equals 2 times the absolute value of x plus 4. Does this look familiar? Does this look familiar? Hopefully you say, yes, this is the same, or looks exactly like point-slope form of a linear function, where you have what? The point. The point would be what? The opposite of what's inside. The opposite of what's inside, which would be what? Opposite of what's next to x would be negative 4, and the opposite of what's next to y would be positive 1. Now, notice, the negative 1, okay, so what are you looking at here? You're looking at what? Nothing more than point-slope form, except this is not linear function, and we don't have a slope here. This is actually called a dilation, okay? This is similar to a linear function in that the negative 1, though, has been moved where? To the other side. So notice, we take the opposite of the 4, but we do not take the opposite of the negative 1 because the negative 1 has been moved over here. It's going to become what? A positive 1. So we don't have to change its value. We can just leave it alone. Okay? Hopefully that helped and did not confuse. But back to the problem. So we take the opposite of what's inside is negative 4, and the 1 has already been moved to the other side, so we just leave it alone. So our vertex is negative 4, 1. Let's go ahead and graph this point. Okay? Negative 4, 1 is here. Okay, and label the vertex. So on your quizzes and your tests, guys, you must label the vertex. The vertex is at negative 4, 1. Okay, so make sure you label this point. Now, this is where we start. And remember, every member of this family looks the same as the parent and follows a similar pattern. Now, with the parent function, we went what? Right 1, up 1, right 1, up 1, right 1, up 1. Now, very similar for this function, except we have a dilation by a factor of 2. So the dilation, let me just be very clear. The dilation will multiply the vertical distances. Now notice, I told you guys already in the last problem, we always go right 1. We always go left 1. That never changes. Left and right never changes. Okay, but this up 1, up 1, up 1. Okay, so instead of going up 1, up 1, up 1, we have a dilation here by a factor of 2. What this means is that all the vertical distances are multiplied by 2. So instead of going up 1, we're going to go up how many? Up 2. Instead of going up 1, we're going to go up 2. Up what? 2. So we're still going to go right 1, but we're going to go, instead of going up 1, we're going to go up 2. So from this location, to graph more points, And to get the function on paper, you guys have to go from the vertex, right 1, then up 2. Do it again. Right 1, up 2. Also, left 1, up 2. Left 1, up 2. And we graph the function. And if you compare this function to the last function, you might say the function got skinnier. Okay, now this is not skinny. Okay, the function did not get skinny, guys. Skinny is what? Left and right. Skinny is what? Domain. Okay, the function did not get skinnier. What happened? Okay, this is domain. Did we change the right one? No, we still went right one, right one, right one. The domain did not change, guys. Okay, dilation does not affect domain. Right, dilation affects range. Okay, dilation, the function did not get skinnier. No, what happened? The function stretched vertically. The vertical distances were doubled. What does dilation affect? Dilation affects what? Range. Okay, so the function stretched what? The function stretched vertically, like a rubber band. Okay, so dilation by a factor of 2. Instead of going up 1, we went up 2. Okay, so right 1, up 2, right 1, up 2. Okay, you have your function. Now we have to do domain and range. So for your homework, you guys will graph the function, then you will write the domain and range. Now domain, okay, domain is what? Left to right, or what? Negative to positive. What is forever left? Let me just erase the vertex here for a minute. I'm just going to put its location here, negative 4, 1. What's far left concept called? Far left is called negative infinity. Far right is called what? Positive infinity. So my question is, way out here at negative infinity, do we have function above us? Yes. Forever left. Does the function go forever left? Yes. The function continues to rise and go to the left forever. If we extend outward beyond the planets, beyond the stars, guys, way out here. Okay, is there a function above us? Yes. Okay, so yes, yes, the function comes from forever left. Yes, 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 yes. Does the function go forever to the right? Does the function go forever to the right? Yes. You say, but it's going up. Well, it's going up, yes, but it's also going right. So it's going up and right. So does the function go forever to the right? Yes. This arrow means that the function continues onward. So where do we have domain here, guys? Do we have a yes, forever left? Yes, 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 we have function. Yes, 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 the function goes forever right. Our domain is what? Negative infinity to positive infinity. Or we have function from forever left to forever right. In terms of the machine, this means that the machine will accept any real number. So looking at the absolute value machine, can we put any number into this machine? Yes. Okay, so negative, for instance, negative 100, way out here. Okay, imagine that this point were far to the left. At negative 100, can we calculate a y value? Yes. If we put negative 100 in, we get negative 100 plus 4 is negative 96. The absolute value of negative 96 is 96 times 2 is 180, 192 plus 1 is 193. So we get a point way up there. Okay, but can any x value go into the function? Yes. So the domain is from what? Negative infinity to positive infinity. Now, range, we start where? Bottom to top. At the bottom, or say negative to positive. At the bottom is the concept of negative infinity. Up top is the concept of what? Positive infinity. So down here, yes or no? Is there function left or right of us down here? Hopefully you say no. The function is up here, guys. Okay, the function is up at this portion of the x-axis. So down here, yes or no? No, no, no. Running up the y-axis, no. There is no function left or right of us. So running up the y-axis, no, 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 no. Yes. What is this? A height of what? 1. What do we look at? We look at the y value of the vertex. The y value of the vertex, or the height of the vertex, is at 1. So the vertex is going to be key for you guys finding domain and range. So we have what? No, 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 no. Yes. Where's this? At a height of what? Height of 1. We have function to the left of us. And then we have what? Yes, 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 forever up. So our range starts at a height of 1 and goes what? Up forever. So we say from 1 to infinity. Do we include the 1? Yes. So put a bracket. Okay. We include the 1 because there is a point at 1 and forever up. Now, here, let's go to the next function. Okay. We're almost done with this. We've done translation, which is the slide. Something's being added or subtracted. We've done dilation, stretch, which something's being multiplied. We now have to do reflection of the flip. Okay, so one more. We look at here. Y equals negative 1/2 times the absolute value of x plus 5. Okay, so I want you guys to pause the video, and I want you to find the vertex, and I want you to do as much with this, graph the vertex on a graph. Let's just start there. So you guys pause the video, find the vertex, and graph the vertex. Okay? Now, hopefully you found okay, so the vertex. Remember that the vertex is the opposite of what's inside. Okay? Inside we have positive 5, so we have what? Negative 5 instead of positive 5, negative 5. And outside, what's outside? Nothing's outside. So what's being added outside? Nothing. So we say that the horizontal means 5 units left, and what's being added outside? Nothing. So we have negative 5 what? 0. Okay, so we described this translation as 5 units what? 5 units. I was supposed to write that for the last one. 5 units left. Okay, so positive 5 means 5 units left. The vertex is at negative 5, 0. So grab this, label it, negative 5, 0. And now we look at what is the negative 1/2. Well, there's two parts to this. You guys see negative 1/2. Circle the 1/2. 1/2 is called the dilation. Okay, and the negative is called a reflection. So two parts to this. So what is the dilation? The dilation is 1/2. Okay, so what does this mean? Going back over here. On the last problem, the dilation was 2. Okay, the dilation was 2. So what did we do with the vertical distances? We took the vertical distances of 1, 1, and 1, and we multiplied them by 2. Since we have a dilation of 1/2, we're going to multiply these vertical distances by 1/2, giving us vertical distances of what? 0.5, 0.5, and 0.5. So instead of going right 1, up 1, right 1, up 1, right 1, up 1, we're going to go right 1, up what? 1/2. Right 1, up 1/2. Right 1, up 1/2. Remember, you always go right 1. You always go left 1. The domain does not change, guys. What happens here? The vertical gets affected. So we go right 1, up 1/2, right 1, up 1/2, right 1, up 1/2. Now, so we're going to be going right 1, up 1/2, right 1, up 1/2. But what does this negative mean? Okay, so negative, reflection. Reflection is what? A flip. Okay, you can think of this as a negative. All it means is instead of going up, you're going down. Okay, so instead of going up, we're doing the same thing going down. All right, so we're going to go, instead of right 1, up 1/2, we're going to go right 1, down 1/2. Okay, do it again. Right 1, down 1/2. Okay, now remember, 2 halves make a whole. We've already discussed this, guys. Okay, right 1 down 1/2 is a half a unit, guys, not a whole unit. Make sure you're careful here. Then right 1 down 1/2. Every time you go 2 units right, you should be a whole unit down. Do it again. Right 1 down 1/2. Okay. Also go left 1 down 1/2. Left 1 down 1/2. And I'm running out of space. Graph the function. At least 5 points, guys. Now, my question is, what happened to the function? Did the function get wider? Okay, hopefully you say no. The function did not get wider. The function did not get wider. This is not domain. Remember, domain is left to right, guys. The function did not get wider. What happened? This is vertical, guys. What happened? Okay, it did not stretch. We call this a compression. Okay, so it flattened. It compressed vertically. Okay, so remember, what does dilation affect, guys? Dilation affects range. So the function either stretches like a rubber band vertically, or it compresses, flattened like a pancake vertically. Okay, so this function compressed vertically. Okay, now we have to do domain and range. I think at this point you guys are probably starting to get maybe hopefully a little more comfortable with it. It's very hard to do this on a video. In class, I ask students to give me feedback, and they're indicating whether they understand or they don't understand. Hopefully you're getting this. So we start way out here, question. We're running along the x-axis. One more time. If you're not getting this, guys, see if you can follow this. Domain, we're running where? We're running along the x-axis. We're answering yes or no. So out here. Forever left. Now, I don't have enough room, but forever left is beyond the camera, guys. Forever left, way out here. Yes or no? Is there function above us or below us? Well, hopefully you say there's function where? There's function where? I'm just kind of extending. There's function where? There's function below us. So way out here on the x-axis, yes, there's function down here. Yes, yes. As we're running along the x-axis, we're answering yes or no. Yes, 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 yes. The function goes forever right. Okay, so is there function below us? Yes, 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 yes. The function comes from forever left and goes what? Forever right. Here, if you extend out, I think it's easier to see. Does the function go forever right? Yes. We're doing this in terms of the x-axis, guys. So the domain is what? We have a yes everywhere from negative infinity to what? Positive infinity. So the domain is from negative infinity to positive infinity. Or what this means is that the machines in this family will accept all real numbers. Anything can be put into the machine, okay, in terms of the machine. Now, all of the functions in the absolute value family have a domain of all real numbers. So all of your homework questions, this will be the domain for every homework question. Okay? Anytime you see an absolute value function in this class, you can assume that the domain is all real numbers, or we say from negative infinity to positive infinity. The symbol is cap R, 2 lines, looks like this. Okay? This represents any number you can think of. Now range, where do we start? We start what? Bottom to top. So down here is bottom to top, from negative to positive. Down here, yes or no? Negative infinity, way down here. Does the function go down forever? Hopefully you say yes. There is function down here. Yes, the function's falling. There's function down here. So there's function left and right of us. So yes, 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 yes. Up, yes. But just past, what do we have? No, no, no. So where's their function? We have function where? Function left and right of us down here. What do we call that concept? We say from negative infinity up to what? We have yes, 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 up. Yes. Just past this point? No. So what do we have? -4, -3, -2, -1. What is this height? This height is what? 0. I said look at the y value of the vertex. So we have from negative infinity up to a height of what? To a height of 0. Okay, so we put parentheses next to infinity. Do we include the 0? Yes, there is a point at 0, so we put a bracket. So we say that the range is from negative infinity up to a height of what? 0. Do we have anything past 0? No, no, no. There is no function up top up here. No, the function is down here. Okay, so from negative infinity up to a height of 0. Okay, now don't do this. Students do this on quizzes. Okay, they write this, 0 to negative infinity. What is wrong with this? I'm circling it. What is wrong with this? Hopefully you say, well, that's top to bottom. Okay, that's correct. Okay, do we write from 0 to negative infinity? Students look at this and try to do their range. They say 0 to negative infinity. Do we go from top to bottom? No, we go from bottom to top, or from negative to positive. So this is incorrect. This is wrong. Okay, not 0 to negative infinity, but rather from negative infinity to 0. So don't get that backwards. All right, one last function and we're done. Okay, one more. Last function is y equals, and you should try to attempt to do this one on your own. Y equals -2 absolute value of x plus 5. Last one. Try to do this one on your own. So pause the video, see if you can find your vertex, find dilation, reflection, okay, and graph the function. Okay. Okay, hopefully you've tried. Okay, the vertex is the opposite of what's inside. Now, is there anything being added or subtracted inside the absolute value? Hopefully you say no. Nothing is being added or subtracted from x inside. So we have nothing. Nothing. No left and right translation. Okay, but 5 is being added on the outside. Remember, we do not change this value. This means 5 units where? 5 units up. Okay, so we have 5 units up. The vertex is at 0, 5. Okay. And we have a dilation, okay? Dilation by a factor of 2. The dilation is 2, and the negative represents reflection. Oh, I spelled that. Reflection. Okay, so dilation is by a factor of 2, okay? And this means what? The vertical distance is, okay, remember on the absolute value parent function, the pattern is right 1, up 1, right 1, up 1, right 1, up 1. So up 1, up 1, up 1. We don't change the right one. So instead of going up 1, up 1, up 1, all of these vertical distances will be multiplied by 2. So instead of up 1, up 1, up 1, we're going to have what? Up 2, up 2, up 2. But instead of going up, because we have a reflection, we're going to be doing this going down. So our pattern is, instead of right 1, up 2, right 1, up 2, right 1, up 2, we're going right 1, because of the reflection, right 1, down 2. Okay, so from the vertex, right 1, down 2. Do it again. Right 1, down 2. And again, left 1, down 2. Okay, one more time. Left 1, down 2. graph the function. And you guys are memorizing patterns right now. Okay, later in the semester we're going to develop this more in depth as far as where this pattern is coming from. Okay, so right 1 down 2, right 1 down 2, left 1 down 2, left 1 down 2. And again we have to write domain. Okay, the domain for all of the functions in the absolute value family is what? From negative infinity to positive infinity. Need I say it again? Left to right, forever and ever. Is there a function out here? Yes, we have function. Yes, 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 yes. From forever left to forever right. Now range, we start where? We start at the bottom. Okay, so down here, negative infinity up to what? To the top, which we call positive infinity. Down here, yes or no, do we have function? Hopefully you say yes. Does the function go down forever? Yes. Okay, so down here, do we have function? Yes, 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 yes. I pause and ask you. Yes or no? Yes, 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 yes. But past this point, what do we have? No, 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 no. So the function's range starts where? Yes, from forever down. So we say the range starts at what? Negative infinity and comes up to what? Yes, 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 yes. To a height of what? Height of, look at the y value of the vertex. Height of what? 5. Do we include the 5? Yes, put a bracket. Again, do not make this mistake on the quiz. Do not write 5 to negative infinity. We are not starting from the top and going down. So do not write 5 to negative infinity. This means top to bottom. This is wrong. We do bottom to top. So yes, 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 up to a height of what? 5. All right. This concludes this video. And hopefully this is the best I can do, guys, with limited space. And domain and range are a difficult topic. We're going to be spending the whole semester trying to learn more about understanding concepts of domain and range and seeing this visually. Okay, but I think the absolute value function is a good function to start. Good luck on your homework, guys. All right.